If you open the Wi-Fi settings on your smartphone right now, you'll likely see a string of 4 numbers, something like 192.168.1.55. We pass by these digits all the time, but it raises a basic question. What do these numbers actually do, and why exactly does your device need them to get online? Every computer already possesses a permanent physical identifier. It's called a MAC address, and it is hard-coded directly onto the device's network card at the factory. But MAC addresses have a strict limitation. They only facilitate local point-to-point communication, allowing physical hardware to talk directly to other hardware on the exact same local network. That creates a location problem. If you disconnect your laptop at home and take that same laptop to a local coffee shop, the physical MAC address on its hardware remains exactly the same, but the device's location on the global network has entirely changed. Participating in the global internet requires a secondary identity marker. To achieve remote, end-to-end communication, devices need a logical address that updates dynamically to reflect their current location. That is your IP address. To us, that IP address appears as 4 simple numbers, but the machine-level structure powering it is much longer. A routing computer processes a continuous 32-bit string of binary. To organize it, these bits are grouped into 4 8-bit bytes, called octets, separated by dots. Finally, each octet is converted into standard decimal numbers, forming dotted decimal notation. Dotted decimal notation is simply a translation tool. It allows human users to read, write, and configure the vast machine-level mathematics required to map a network. As detailed here, every IP address performs 2 jobs. First is the network ID, identifying the specific shared local network the device is connected to. The remaining portion is the host ID, which uniquely identifies your specific device within that shared network. Map this directly to a physical neighborhood. The network ID is a shared street name, and the host ID is a unique house number. Addresses 192.168.1.55 and 192.168.1.34 live on the exact same street, 192.168.1, that occupy completely different houses. An IP address is a structured 2-part map of relational proximity designed to keep local networks organized. But there is a missing piece of logic here. How does a routing computer actually know where the network street ends and the host house number begins? Looking at this chart, we see the historical method used to draw that boundary, known as IP classes. By reading the value of the very first octet, routers categorized addresses into rigid classes, A through E, which dictated the exact mathematical split between network and host. Today, computers rely on a secondary configuration value called a subnet mask. This is a companion number, like 255.255.255.0, that tells the machine precisely which bits belong strictly to the network. Network engineers also use CIDR notation, a modern classless shortcut. A slash followed by a number at the end of the address explicitly counts out the exact number of network bits from left to right. Without these specific boundary rules, the binary numbers would blur together, rendering the IP address useless for routing data. When you zoom out from a local Wi-Fi router to the scale of the global internet, the necessity of this structure becomes clear. Every single packet of data sent across this fast internetwork must carry both a source and a destination IP address. Routers read these addresses end-to-end. They rely entirely on those strict network and host divisions to guide each packet flawlessly to its target. The next time you spot those 4 decimal numbers on your Wi-Fi screen, recognize them as your exact logical coordinate, the mathematical location preventing digital chaos in a universe of billions of devices.